Okay, hi students, good morning. Today we are going to discuss the second chapter of electrostatics, that is electrostatic potential and capacitance. First chapter, electric charge and field, we have completed. In that first chapter, electric charge and electric field, we have studied it. Electric field E. Electric field is a character of charge. If there is a charge, there will be a field around it, right? So these are the things we have discussed in the previous class, and now the concept is potential and capacitance. However, capacitance is a second bit of this chapter. Now our discussion should start from potential. It is. See, before going to the concept, I would like to revise two things from the previous chapter. In the previous chapter, regarding two forces, one is Coulomb force, another is gravitational force, we have studied it, right? Regarding the electric charge and field. See, if there is a charge, means between the two charges, the force of attraction or repulsion, that we have explained successfully by Coulomb's force it is. So Coulomb's force, it is a conservative force like gravitational force. See, Coulomb's force, it is stated between the two charges. Like that, gravitational force is also a attraction force that is stated between the two masses. The only difference is Coulomb force can explain the force of attraction as well as repulsion between the two charges. This force of attraction between the two masses is explained by gravitational force. Right? See, these are the things we have discussed in the previous chapter. See, now our discussion is related to this. So that is why I am revising. Say, for example, if it is a gravitational field, if it is a gravitational field, on the surface of the earth, anywhere you can go, there is a gravitational field is present on everywhere. So that if I will drop any object from the certain height from the surface of the earth, all the object move towards the surface of the earth. It is because of, we know that it is because of gravitational force of attraction between the two bodies. See, while I am dropping the object from the certain height, the object will move with certain energy. For example, 100 meter per second, this object is moving towards the earth to a height h. 100 meter per second is what? Kinetic energy. If I will take another object, if I will drop from here, let us assume this height is h2, this is h1. For h2 height, let us assume this object is moving with 200 meter per second towards the earth. Which object is having more energy here? While dropping the object from this point, the object is having 200 meter per second, and from this point the energy is having 100 meter per second. 100 meter per second, it is a kinetic energy. If we convert that, we will get some joule. See, what I am dropping the object from this point, that is having 100 meter per second speed. The same object, if I will drop from here, from this point, the same object getting 200 meter per second speed. That means that a different speed or a different energy, what we are getting to the same object, that is depend on the location. Potential energy of the object is equal to mgh. It is depend on height only it is. So because of the height, the object from this point 100 meter per second it is getting, the same object from this point 200 meter per second is getting. So this potential energy, it is depend on the potential energy of this object, it is depend on height only it is. So potential energy of the mass in a gravitational field, it is depend on height only it is. So how we have defined this energy, how we are getting different energy or different speed to the same object at a different points. the same potential energy, the same potential I am going to define between the two charges. Between the two charges. So, see here, our concept is potential. In the previous chapter, electric field, we have studied that electric field is a character of charge. Electric field is a character of charge. If there is no charge, there is no electric field. At the same time, now potential is related to energy. Electric field is related to force. If there is a charge, there will be an electric field. If there is a charge, there will be an electric field around it. If there is electric field is there, means if any new charge will enter in this region, this charge will experience the force. That means electric field is basically what? Force only it is. Electric field is basically force. So electric field definition, electric field is equal to F divided by Q. So F is equal to Q into E. How much force experience this charge? Q into E. Q into E due to this electric field. Due to this electric field. Right? So electric field is a character of charge and electric field is basically force it is. Electric field basically it is a force. Now our concept is potential. Potential is related to energy. How it is, we will discuss. See, I will take a charge at this point and I will check the energy of this charge. It is, let us assume, 100 joule. I will take the same charge to this point, from here to here. Now this time I will check the energy. On checking the energy at this point, I am getting 50 joule. I am getting 50 joule. So on taking the charge at this point, I am getting 100 joule. The same charge if I will bring here, at this point, I am getting 50 joule. How it is? What is the reason? The question will arise, right? See, to the same phenomena, I will take this charge to this point. At this point, I will bring here. To this point, this is a point or place. To this place, I will bring from here to here. So here, let us assume I am getting 10 energy to that charge it is. So by this observation, same charge, if I will place here 100 joule I am getting on checking, the same charge if I will bring here 50 joule I am getting, the same charge if I will take here 10 joule I am getting. To the same charge, different energies I am getting to the same charge. By this observation, I can say that the energy of the charge, it is depend on the location. It is depend on the location. How? The speed of the moving object towards the earth, it is depend on the height. Like that, in the same manner, I am getting this observation. To the same charge only. If I am placing this charge at this point 100 I am getting, on placing the same charge from here to here I will bring, at this time 50 I am getting. If I will bring this the same charge here, 10 joule I am getting. By this phenomena I can say that the potential or the energy of the, say, potential is related to energy it is. So 100 joule, 50 joule, 10 joule what I am getting, this is the character of location it is. This energy, different energy what I am getting to the same charge, there is a character of location. It does not depend on the charge. Two same charge, same magnitude charge I will take, one charge I will place here, another charge I will place here. What I will place the first charge Q1 acquires 100. What I will place the second charge Q2 acquires 50. On observing I am getting here. So for the clarification purpose, I will take Q2 here and I will bring Q1 here. Again Q2 on bringing here, Q2 will acquire 100 again. and on taking this q1 here, again q1 is getting 50. That means it does not depend on the charge, it is depend on the location. It is by this observation I am getting how we are getting different speed at a different points on dropping the object from the different height, how we are getting the different potential energy. I am getting different energy of the charge at a different locations. So potential, what it says, potential, it is related to energy. So potential is a character of location, character of location point. The potential of this charge at this point 100, the same charge I will take here, the potential of this charge at this point 50. So it is the character of location, potential of this potential of this charge, it is a character of location. On changing the location, different energy is acquiring by the charge. So potential is a character of location, I can say that by this observation. And say on changing the positions from here to here, here to here, or here to here, here to here, on changing the position, different energies getting by the single charge. So one more conclusion I can say that by this discussion, that is potential is a possibility of achieving energy, possibility of achieving energy. See here 10 at this point I will take the charge at this point, at this point 10 joule getting by this charge. The same charge I will take here, 50 joule is getting, on checking I am getting 50 joule. The same charge I will take here, to the same charge 100 joule I am getting on checking the energy of this charge. That means possibility of achieving the energy, and that is depend on the location, location. See where is the potential is more among these 3 points? Easily I can say that at this point the potential is more, at this point. See, to understand the concept how the potential is a character of location, I am telling, to understand the concept of potential and how it is depend on the location. So I would like to give a simple example on this. See, the potential word in our day-to-day life we will use. I would like to give a simple example on this. That is, say for example, if I want to open a bookstall, first I will think over the place where I should open the bookstall, where the potential is more. So later I will decide I should open the bookstall in front of colleges or nearer the colleges it is. So the rate of business is more at that particular point. If I'll open the bookstall out of the city, the rate of business is too less. That means their energy, potential, money is less out of the city. If the same bookstall, if I'll open in front of the college or nearer the school colleges, the rate of business is more, energy means money is more, like that it is. The simple example it is. So it is depend on the what? Location. It is depend on location. So potential is a character of location point it is. Where the charged particle is there. Depend on that the energy is decide here. Right? So that potential is a possibility of achieving the energy. See, this is the concept of potential. Now, I am going to define potential energy. Potential energy. See, now the concept is potential energy I am going to discuss here. Potential energy is a is a, say, potential is a character of what? Location. And potential is possibility of achieving the energy. How it will achieve? On shifting the charge from one point to another point. One point to another point. Like that, say, potential energy is a characteristics of a charged particle. Charged particle. It is a characteristics of a charged particle while moving from one point to another point. Right? See, charged particle is placed at that point. From here to here I will place the charge, means 50 you will get. From here to here I will place this charge, the same charge will get 100 joule. That means the energy decide on the location it is. So potential energy is a characteristics of a charged particle. Placed at that point where you want, how much energy you want to give the energy to the charge. Depend on that you have to fix the place. Right? How we are deciding the location to open the bookstall, like that it is. The similar example it is, right? So this is the concept of potential energy. Now I will discuss the concept of potential energy by taking one simple discussion. Okay, see here. See, I will take a charge Q at a point A. Another point is there here, or location, that is B location. At location A or at a point A, I have placed the charge Q. See, whatever the things we are discussing all about this is under the electric field only, because if there is a charge, regarding the charge we are discussing means the electric field is there around it. Just you try to remember this, right? Our discussion is in electric field only it is. Now see here, everywhere the electric field is there. Regarding this we will start the discussion. See, this is the what direction of the electric field. Under that, at a particular point A, I have placed the charge Q. Now, at this point, let us assume some amount of energy is there already. That is 10 joule. And see, from this point to this point, I want to shift this charge. To shift the charge from here to here, we have to apply the force on the charge in this direction. How much force we need to apply here? See, already this charge is experiencing the force due to the electric field. I said electric field is basically force. Electric field exerting the force on this charge. Electric field E is equal to F divided by Q. How much force? F is equal to Q into E. Q into E amount of force is exerting on the test charge or this charge Q. See, in this direction. So, to hold the charge to this point, I have to apply the same amount of force in the opposite direction. So, at this point, this charge is having, let us assume, 10 joule. So now I want to move the charge from point A to B against the electrostatic force of repulsion. Say there is a force of repulsion between electric field lines and this charge. This charge is, let us assume, positive Q or plus 1 it is. So plus and plus which repel each other. So against the force of repulsion, I want to move the charge in this direction. That means I have to apply the force almost equal to the electrostatic force, Fe it is. Fe means electrostatic force. So almost equal force I need to apply. And the question you may arise here, that is, can we apply the force greater than this QE? We can't apply the force on the charge greater than QE, because if we apply the greater force on the charge, the displacement will take place very fast. So with respect to time, the displacement goes on changes. As the displacement changes, the acceleration of the particle increases. Acceleration means F is equal to ma. Acceleration will increases. If acceleration goes on changes, A goes on changes means F also goes on changes. So I can't find the work done at this time. At this time I can't find the total work done from point A to B. So because of this reason, what I will do, just I will apply the force almost equal to this. So on applying the almost equal force, this charge will displace through a very small displacement, very small, that is dx. So our aim is to shift the charge from here to here without accelerate. See, without acceleration, I want to shift the charge from here to here, right? So that is why I am applying same amount of charge, same amount of force, that is F external is equal to QE. That is almost equal to Fe is equal to QE. Fe stands for electrostatic force. So on applying F external is equal to QE force on the charge, small amount of displacement, very small amount, it is very negligible, it is, that is dx. I have taken it as dx is the small amount of force it is. Let us discuss what I have discussed. Just see, if the point charge is displaced from here to here, on displacing the position from one point to another point, the work will done on the charge. So that work done I will define here. See, that work done I will define. General definition of work done is equal to force into displacement. This is very small displacement. It is not considerable. It is negligible displacement. It is such a displacement because our aim is to shift the charge from here to here without acceleration. That is why I am applying equal amount of force. Right? That is very much important. When the charge reach from here to here, I will apply again same amount of force. Let us assume here it will come. Again I will apply continuously on shifting the place from one point to another point with a negligible distance. I will apply the force at every point with the same force. That is very much important because the acceleration should not increase. As the acceleration increases, F value change. If F value change with respect to time means we will not get the work done exactly on changing the F. So F we need to fix. So that is why it is. So first I will define the work done to this small displacement. Later I will integrate to the whole displacement. Right? Work done is equal to force into displacement. Which force it is? External force. Because of the external force only work is done on the charge. The charge shifting from here to here. Now finally let us assume the charge came here. Let us assume the charge came here. Now integrating work done from A to B is equal to work done from A to B is equal to integration A to B F external dx. Okay, now since we know that this electrostatic force is equal to this F external, so F external is equal and opposite to electrostatic force. So I will write this equation WAB is equal to, see, integration of A to B, F external means minus FE, minus FE means electrostatic force into dx. Electrostatic force, how much it is? FE is equal to QE, right? See, that I will write again, WAB is equal to A to B minus FE minus Q into E. FE means we have force. This dx as it is. And this equation I can also return as WAB means work done from A to B. It is WAB means work done from A to B. Okay. Minus Q. I will take outside, and A to B E into dx. This is what we got here, work done. See, from the work energy theorem, we know that from the work energy theorem, work done is equal to change in the kinetic energy, and work done is equal to change in the potential energy. We have proved it. So, from work energy theorem, I can write work done from A to B is equal to change in the potential energy. See, here what is the energy of the charge at a point A? 10 it was. Now, here it is, let us assume 20. So, energy, potential energy, I will denote by U. So, work done is equal to work from the work energy theorem, UB minus UA, change in the potential energy. The method to write the change in the potential energy, higher minus lower, higher energy at point B minus lower energy at point A, means final minus initial it is, that you will get a difference. Say for example 20, 10, what is the difference? 10 it is, 10 joule is the difference, it is potential energy difference between the 2 points. That means this 10 joule energy is required to move the charge from here to here. That is. Anyhow, see here. Now, this is one more relation. WAB is equal to UB minus UA. And this equations I can write UB minus UA is equal to WAB. WAB is equal to what we have here? What we have? Minus Q integration A to B E dx. Right? See, this is potential difference energy. Potential difference energy. Potential at A is 10, potential at B is 20 joule. 20 and 10 difference is 10 it is. 20 and 10 difference is 10 joule. That means 10 joule is needed to do the work from point A to point B. And that is equal to, we got this equation. So that, see here, to this equation I will divide by the charge Q. Because, why it is? Because I am going to divide this Q. Whatever the work is done, that is to this charge only it is. So, that is why I am dividing this charge. Okay, see here, that I will write here. See, just I will remove this. Okay, see. The equation I will write UB minus UA divided by Q. Just these are the what discussions. WAB divided by Q, and that is equal to minus Q. However, I am going to write divided by Q. No, Q and Q get cancelled. This Q and divided by Q. Remaining I will write as it is. A to B E dx. Right? See what it shows. Physical meaning of this. WAB, work done per unit charge. work done. If work is done means the point is shifting from, the charge is shifting from one point to another point. That is what potential difference. If work is done